At its core, string theory proposes a revolutionary idea. The fundamental building blocks of the universe aren't particles, but tiny vibrating strings of energy. Imagine a violin string. The way it vibrates determines the note you hear. Similarly, the way these tiny strings vibrate determines what they become: an electron, a photon, or even the particle that carries gravity, the graviton. This is where string theory diverges from traditional physics. Instead of particles being point-like dots, it envisions them as one-dimensional strings. This perspective resolves many of the inconsistencies in modern physics, especially when dealing with gravity at a quantum level. In essence, string theory tells us that the universe is a vast symphony, and every particle is a note played on the tiniest of strings. In the next section, we'll explore why scientists developed this idea in the first place. What problems were they trying to solve? Stay tuned. What if I told you that everything you know about the universe, planets, stars, even you, is made up of tiny invisible strings vibrating in endless dimensions? This is string theory, a groundbreaking idea that could unlock the secrets of existence itself. It's bold, it's controversial, and it might just change how we see reality forever. In today's video, we'll unravel this mind-bending theory, explore its promise as the ultimate theory of everything, and discover why it has physicists both excited and puzzled. Is string theory the key to understanding the universe, or just a beautiful dream? Let's find out. Why was string theory even needed? To answer that, we need to look at one of the greatest challenges in modern physics, uniting general relativity and quantum mechanics. General relativity beautifully describes the universe on a grand scale: planets, stars, and galaxies. But zoom into the quantum realm, and its rules break down completely. For decades, physicists have struggled to find a theory of everything. A framework that unites the massive with the minuscule, gravity with quantum particles. Enter string theory. By replacing point-like particles with tiny vibrating strings, it offers a way to bring these two worlds together. Strings create a natural bridge, allowing gravity and quantum mechanics to coexist in a single elegant framework. It's an ambitious idea, but it's not without its challenges. And yet, string theory has sparked decades of research, offering hope for a unified understanding of the cosmos. Next, we'll dive deeper into these strings. How do they work? What makes them so revolutionary? Let's unravel the details. So, how do these strings actually work? Imagine each string as a tiny loop of energy, smaller than an atom. So small, in fact, that if an atom were the size of the solar system, a string would be the size of a tree. The secret lies in their vibrations. Each unique vibration creates a different particle. Fast vibrations might produce a photon, a particle of light. Slower vibrations, maybe a quark, the building block of protons and neutrons. But strings don't just vibrate, they can split, merge, and even form loops. This allows them to describe all the interactions we see in nature. From the force of gravity to the electromagnetic force and beyond. What's truly groundbreaking is that this simple concept of vibrating strings could explain everything we see in the universe. It transforms physics into something almost poetic, a cosmic dance of energy, shaping reality itself. Next, we'll explore a crucial question. If strings are so fundamental, where do they fit in the grand structure of the universe? Let's find out. If strings are the building blocks of everything, how do they fit into the grand structure of the universe? Let's break it down. At the smallest scale, strings vibrate to create elementary particles like quarks and electrons. These particles form atoms, which then combine to make molecules. And from there, everything we know, planets, stars, galaxies, comes into existence. But it's not just matter. Strings might also hold the key to the very fabric of spacetime itself. According to string theory, the vibrations of strings could weave spacetime, connecting quantum mechanics and the force of gravity. In this sense, strings aren't just particles, they're the threads that stitch together the universe at every level. If true, String theory could redefine our understanding of what the universe is and how it works, from the tiniest particle to the vastness of space. Up next, we'll explore one of the most fascinating predictions of string theory: the existence of hidden dimensions. Could there be more to the universe than we can see? Stay tuned. What if the universe has more dimensions than we can see? String theory predicts exactly that. Hidden dimensions, folded and compacted, existing alongside the three we know: length, width, and height. These hidden dimensions aren't vast like the ones we're familiar with. Instead, they're curled up at incredibly small scales, like intricate patterns woven into the fabric of spacetime. One of the most famous concepts in string theory is the Calabi-Yau manifold, a shape that describes how these extra dimensions might be compacted. The way strings vibrate through these hidden dimensions determines the properties of particles, like their mass and charge. These extra dimensions aren't just theoretical curiosities. They might hold the answers to some of the biggest questions in physics, like why particles behave the way they do, or why the universe works as it does. In the next section, we'll dive into the ambitious idea that string theory isn't just about one universe. It might explain the existence of many. Welcome to the multiverse. What if our universe is just one of many? String theory opens the door to this incredible possibility: the multiverse. According to string theory, there could be countless universes, each with its own set of physical laws, particles, and dimensions. This happens because string theory relies on a concept called the landscape of possibilities. Each way the hidden dimensions fold or compact themselves creates a different universe with its own unique properties. In one universe, gravity might be stronger. In another, stars might not even exist. This raises fascinating questions. Are we just a tiny part of an infinite cosmic mosaic? Could there be versions of reality where life exists in ways we can't imagine? While the multiverse is a controversial idea, it pushes the boundaries of what science can explain and forces us to rethink our place in the cosmos. Next, we'll tackle a key question: how do scientists test such an ambitious and abstract theory? Can string theory ever be proven? Let's find out. String theory is elegant, ambitious, and groundbreaking. But here's the challenge: how can we test something so abstract and microscopic? The strings predicted by the theory are unimaginably small, so small that no current technology, not even the most powerful particle accelerators like the Large Hadron Collider, can detect them directly. However, scientists are looking for indirect evidence. For instance, the vibrations of strings might leave subtle imprints on the behavior of particles, or the distribution of energy after high-energy collisions. Another possibility comes from the universe itself. String theory predicts phenomena like extra dimensions and unique patterns in the early universe's radiation, the cosmic microwave background, that could someday be observed with advanced telescopes. Testing string theory isn't easy, and some argue it might never be fully proven. But every scientific breakthrough starts with bold ideas, and string theory continues to inspire experiments and innovations. In the next section, we'll look at why string theory, despite its challenges, remains such an appealing framework for physicists worldwide. Why do so many believe in its potential? Let's explore. With so many challenges and unanswered questions, why do physicists still believe in string theory? The answer lies in its elegance and potential. First, string theory is the only known framework that can unify all the fundamental forces of nature: gravity, electromagnetism, and the nuclear forces. By describing particles as vibrating strings, it offers a consistent way to combine quantum mechanics with general relativity, something no other theory has achieved. Second, string theory isn't just a theory of particles, it's a theory of space-time itself. It provides insights into the fabric of the universe that no other approach has been able to offer. And then there's the mathematics. String theory's equations have led to unexpected discoveries, like the idea of black hole entropy, which connects thermodynamics and quantum mechanics in a profound way. For many physicists, string theory is too beautiful and too promising to ignore. Even if it's not the final answer, it's paving the way toward deeper understanding. In the next section, we'll dive into the criticisms of string theory. Why do some scientists argue that it's more philosophy than science? Let's explore the controversy. Despite its elegance, string theory has faced significant criticism over the years. Some physicists argue that it's more philosophy than science. But why? One of the biggest issues is testability. The strings in string theory are so small, far beyond the reach of current experiments, that direct evidence may never be possible. Without experimental confirmation, critics argue, string theory risks becoming purely theoretical speculation. Another criticism is the sheer number of possibilities string theory creates. The so-called landscape of solutions, with its countless potential universes, makes it difficult to make specific, testable predictions. Some even question whether string theory is truly science. If it can't be tested or falsified, is it a scientific theory or something else entirely? But even its critics agree on one thing. String theory has sparked groundbreaking ideas and challenged the limits of human understanding. Whether it's right or wrong, it has pushed science forward in unexpected ways. In the final section, we'll reflect on what string theory means for the future of physics and our understanding of the universe. Is it the key to everything, or just the beginning of something even bigger? Stay with us. As we look to the future, one question remains. Where does string theory go from here? String theory has already transformed the way we think about the universe, but its ultimate role in science is still uncertain. Some physicists believe it's the key to a complete theory of everything, while others see it as a stepping stone to something even greater. With new technologies on the horizon, like more powerful particle accelerators and cutting-edge telescopes, we may soon uncover indirect evidence for string theory. These tools could provide insights into hidden dimensions, quantum gravity, or the fabric of spacetime itself. But string theory isn't just about solving equations. It's about expanding our imagination and understanding. Even if it's not the final answer, it challenges us to ask deeper questions and to dream of what might lie beyond our current grasp. The journey of string theory is far from over. Whether it proves to be the ultimate truth or a stepping stone, one thing is clear. The pursuit of understanding our universe will continue, driven by the same curiosity that led us to explore string theory in the first place. Thank you for joining us on this incredible journey. If you enjoyed this exploration of string theory, don't forget to like, share, and subscribe to Astrofynity Horizon for more dives into the wonders of the cosmos. The universe is vast, and we've only just begun to unravel its secrets. As we close our journey into string theory, let's take a moment to reflect. This theory isn't just about equations or abstract concepts. It's about the quest to understand the very essence of existence. String theory teaches us that everything, from the tiniest particles to the vastness of the cosmos, might be connected by a single, elegant framework. It's a reminder of how much we've learned and how much we still don't know. The beauty of science lies in its ability to inspire. Whether or not string theory is the ultimate answer, it pushes the boundaries of human imagination and fuels the desire to explore. The universe is vast, mysterious, and endlessly fascinating. And while we may not yet have all the answers, every step we take brings us closer to understanding our place within it. Thank you for joining us on this incredible adventure. If you enjoyed this deep dive into string theory, don't forget to like, share, and subscribe to Astrofynity Horizon. Together, let's keep exploring the cosmos, one discovery at a time.